Good afternoon. Today, me, Karol and Piotr shall present the results of our project for the Team Machine Learning project course concerning video generation. The project was done under the supervision and guidance of Dr. Biliński. First, we shall introduce our project, describe our research goals and objectives, and how we've decided to approach them. Thereafter, we will provide some preliminary information and move on to the crux of the presentation, that is to say, our contributions and improvements we've implemented. Last, we'll sketch out some of the modifications that didn't pan out. As the title suggests, the subject matter of our project is, in the broadest sense, the task of video generation, which, similarly to the task of image synthesis, has been experiencing strides in recent times. In particular, we focused on the following aspect thereof. First, synthesis of videos without any prior knowledge or conditioning signal with respect to either appearance or motion. Second, learning a disentangled representation of video content vector, in particular splitting texture, appearance, and other static attributes of objects in video, and motion thereof, allowing for independent manipulation of both. And third, improving quality and length of generated content, which so far has been lackluster. Finally, conditional video generation, to allow for manipulation of generated video content. We have decided that, in order to achieve these objectives, the best course of action would be to improve upon an existing suitable video generation model. There are many promising existing solutions which we've investigated, and after a period of deliberation, we've decided to use StyleGAN-V, a model introduced in the paper StyleGAN-V, a continuous video generator with the price, image, quality, and perks of StyleGAN-2 by Skorohodov et al. From 2021, which was published at the CVPR conference in 2022. There are many and varied reasons for selecting StyleGAN-V as our base model over other options, which we would like to point to now. It's a top-tier video synthesis model which has, at the time of publishing, demonstrated major quality improvements over previous approaches. Another major factor in our choice were design considerations, since our mode of investigation necessitated fast development cycle and rapid testing of our ideas and tweaks. StyleGAN-V can be trained from scratch in under 2 days on a Model 4 GPU node, far less than the competitors. Finally, the comparative simplicity of the architecture suggested to us a large potential for improvement and possibility for developing avenues for enhancing it. Here, as an example, we can see videos generated by the baseline model. We can see high level of visual detail and temporal coherency exhibited by the solution. And here are the quantitative results obtained by the model compared to a number of alternatives. The FVD16 and FVD128 symbols denote freshet video distance, a widely used metric in the field of video generation. Lower numbers denote better performing models. The evaluation has been performed by the authors in datasets containing videos of faces, skies, and actions performed by humans, among others. As we can see, StyleGAN-V achieves superior performance on the vast majority of the benchmarks, whilst taking far lower computational resources to train. Before we speak of our modifications and contributions, it is necessary to sketch out the baseline architecture. StyleGAN-V is an example of generative adversarial network. In it, the generator of videos is trained with the help of a discriminator, designed to distinguish between real and generated samples, thus providing the necessary training signals for the former. In more detail, it can be thought of as an adaptation of StyleGAN-2 architecture by Karas et al., which generates images to the domain of videos. It does this by adding temporal information to the generator and making the discriminator operate on frame sequences instead of solitary images. The frames need not be consecutive, as is the case in other architectures, thanks to embedding the timestamp. Because of this, computational requirements are lax, We will see the components of the model in greater detail on the next slide. Before us is a schematic of Stargand V's generator. It follows the design of Stargand 2 with the progressive upsampling by synthesis blocks and the inclusion of latent content vector, with the addition of making the input of the model, seen at the top of the diagram, be a function of the time step associated with the frame to be generated and the motion vector, seen in the middle left section. This setup, though fairly simple, achieves impressive results as we've seen. Moreover, the scheme of generation, wherein we do not generate entire frame sequences but rather generate frames based on time step, makes the generator equivalent in performance to the base image generator, despite the ability to generate motion. And, as a counterpart to the generator, here's the discriminator, which outputs whether the sample frames shown atop the image are real or fake. The architectural innovation, which further improves computational efficiency, is delayed fusion, whereby we process the frames separately and only concatenate the more compact features in the end. Embedding time differences allows the architecture to be trained sparsely, that is, without having to generate consecutive frames.
During our initial research, we attempted to reproduce the results from the mentioned baseline. Unfortunately, what we found was that the reproduced results were significantly worse than what was claimed in the paper. Naturally, we wanted to get to the bottom of this discrepancy. So we reached out to the authors of the paper for clarification. However, they informed us that they are not sure why, and at the moment they do not have the time to look into it.
So now we will talk about the modifications that we did to StyleGAN video architecture. We made a couple of simple changes to the StyleGAN video model and got significantly better results. The first change involves integrating the temporal shift module into the discriminator at every block before concatenation. The temporal shift module is a powerful technique for video understanding. It achieves the performance of 3D convolutions while keeping things simple like 2D convolutions. PSM works by shifting some channels along time dimension, and it helps to exchange information between neighboring frames. And this module can be easily added to any 2D convolution backbone to make it able to model temporally without any extra parameters. And as you can see in the table, the modification led to substantial metric improvement. Next, we explored the sampling procedure. The authors stated that sparse training yields superior results, implying that fewer sampled frames produce better results. For us, this claim was very counterintuitive, and it prompted us to investigate this issue. The authors used random sampling with k equals 3 frames processed by the model. An additional parameter was the maximum distance between 2 frames, and it was set to 32. And when authors did the ablation study, they did not change the hyperparameter M, and it led to denser sampling when K was increased. So this reduced the variety of the data available to the discriminator due to the similarity of neighboring frames, because the more frames, if the frame is very close to another frame, then basically these 2 frames are the same. So our straightforward solution was just to increase M while increasing K, and not necessarily linearly. We just simply experimented with various M combinations. We believe that further can be done to change the sampling technique to generate even better results. And as demonstrated in this slide, when increasing M with K equal 8, we saw nearly double the improvement in terms of metrics. And with these two simple modifications, so the first resolving the sampling issue and second integrating TSM module, we achieved state-of-the-art performance in phase generation based on FVD metric.
So later we decided to focus on another task, namely disentanglement of motion and appearance. To do this, we utilize clip model in StyleGAN-V architecture. Basically, we can take any photo and embed it into our model, which can be later used by fine-tuning clip model for a given example to match the given prompt. For instance, here we can see Elon Musk with a blonde hair. One intriguing aspect that emerged from using the clip model with StyleGAN-V is the aforementioned disentanglement between appearance and motion. What does this mean? Essentially, in our case, we can alter the appearance of an object or a character in a video while keeping the motion consistent. Here on the right, you can see 3 different rows with 3 different prompts, where we can see that indeed the clip model changed the appearance of generated faces. And that's all. Thank you for your attention.